Hello everyone. Here we are going to start with the model 2 and the first one is the lecture 1. Here we are going to deal with the mainly with the geometrical representation of the signals. So before getting here, so you need to have some brief idea of what we have done in the previous lecture. Initially we started with the model 3 where the different type of modulation, the signal how is to take and how is to represent it, we saw there. In the model 4, when you send this modulated signal into the channel, what all the condition and the criteria it was to be met, it has studied, was look into it. And the 5, we had a brief idea about the spectrum, how the utilization of the channel, and from there how is to utilize the application. For example, the different type of spectrums, and one more thing is like we saw some of the different PN type of sequence, like PN sequences, everything we saw that. Then in the model 1 we saw some of the factors which can be implemented and the different type of envelopes, like Hilbert transform. We saw how is to interpret the signals, and we studied about um, the pre-envelope, all those kind of stuffs and the complex representation. Then we had a, in short, we discussed about the different type of line coding. But why do we require this pre-request here is that we can have a regarding the we can say like to represent the signal in the different dimension, or we can say it as a geometrical representation. So we know how signal has been modulated and how signal has to be generated and how signal would be transmitted, but how to represent the signal if it is presented in the different planes. So that concept will be mainly will be dealing here. So if you go through in the sequence of 3, model 3, model 4, model 5, model 3 and model 5, model 4, then model 1, and then come to the model 2, you will understand the application of each of the signal and how to represent it there. So now we'll start. First we'll look at the introduction here. So what is this? We'll have a brief idea about the digital communication, how this transition from the local present signal we can be converted there. So locally what is present the signal is the analog communication. Analogly what we speak now, what I'm speaking also is the analog signal that is converted into the electrical signal by a mic, or which is like going to take us receive the signal. It is going to convert that value into the electrical pulse, and that is given to the one part, and that is going to record like that. This is what we think. For example, if you take a like this a waveform, okay, if you take a waveform like this way, and if you divide it like this way, this we call as a sampling there. And now like this we are going to take the values there. Now this is we call as a sampling process usually, and the maximum peak available here, that value will be noted down here, and here this value, and here this maximum value will be estimated, and this estimation process we usually call it as a quantization. And this we have learned in your previous semester, the principle of communication system, where we used to quantize sampling and quantization levels, and all this process, the conversion of analog to digital conversion, in the model 5 most probably. And this conversion is we call how it is converting the first process, that is, it is the signal whatever is there is been represented in the form of a coded pulse. Like this will the coded pulses it will be represented, and then it is going to convert this estimation process into quantization level. This is how it is. This line means the analog waveform has been converted into the coded pulses, and that represents the transition of analog communication to digital communication. The maximum value what is there is been taken there. This transition has been empowered by several factors. First one, ever increasing advancement of digital silicon chips, digital signal processing, and computers. So we need not explain more on this. We know that nowadays how the mobile was. The very good example is our mobile. The when it started, it was some kind of a basic mobile phone. It used to say only for calling and messaging, a black and white sets. Now we everyone has a smartphone mobile phone, which can be used to edit a word, to camera, record, video record, Facebook, attend a online class, watch YouTube videos, everything it is possible. So that is the strength of the processor which has been digitized now. And this digitization has increased the strength of the processor, increased the strength of the processor, and that is making that a small minor processor. We know the laptop. Now again the same power can be done in our smartphones. So this is what was the advancement of the digital silicon chip, digital signal processing of a kind of hearing a voice, recording, CD, USB, everything that we can call is there. But I'm taking about the practical examples. If you take it in a digital signal processing, like what we use in the forensic science and all, that all, and the computers, how before how it was, the now the how it is going on, the computer to the laptop, laptops to the netbooks. Now everything, notebook to netbook, everything has been advanced now. So again, which has been prompted further enhancement in the digital silicon chip. So thereby it is improving everything. So today's mobiles, today laptops is not is date bar after 1 year. So it becomes old now. Then it's improved reliability, which is afforded by the digital communication, is much greater extent than it is possible with analog communication, as we all know that, because the reliability of the digital communication is like that, from the transition from the DTH to mobile phones to TVs and all, everything. Now a TV can be utilized to, for example, you can even browse it, you can watch everything you can do in a TVs, we call as smart TVs, like that. We can rely on those things. And also we can use a VoLTE, we can use a video calls on a live, we can conference the call, all those things. The broadening range of multiplexation of users. So this is where we use the conference calls, etc. Too much also we can use it here. So we can use a multiple users and all. We can have a good strength, the signal strength, and we can use this kind of we call as the digital modeling techniques. So we have studied in our the model 3. Then the communication network. So this is where how to understand. For example, if we can broadcast or screencast, laptop to mobile or mobile to TV, everything we can do. So there are different layers or the protocols which will be used there. So how to make two systems to use, like a two independent system to rely, make it as one as master and another slave. Like we can transmit a data from one to another. So this is how a system talks with each other, like how we talk with our friends. So this is what one other form of a use. This is a very good use of that. Now you can have a brief in a detailed study in your 7th semester where we have a computer networks there. Okay, computer communication networks there. This is the usually a preferred choice there, where we can also see the packaging transfer, data transfer, the different protocol layers, etc., etc. We can understand that. Now, after a brief idea, we'll have what is digital communication system. You'll come to know that. A typical model of a digital communication system is this one. This is a message source, what we know. This is like some kind of an analog or something signal, like anything is there. But as we are using a digital communication system, it should be a message source in the digital communication only, like bits of zeros, one, etc. It should be a binary bit. Then it has been transmitted to the vector transmitter. So what is this vector transmitter? Another question arises. Vector is what? We have a representation of data in different planes there. As we usually represent in terms of x, y, z planes there. Then after representation of x, y, z plane, then this we call, might be a signal might be in different planes and or 2 or 3 planes and all, it can be there. And this we call as a SI. So SI means SX in X plane, SY in SY plane, SZ in the Z plane. So this everything is we call the vector transmitter. It is going to send this data into different planes and it is going to the modulator. This modulator modulates the signal. So this we know. Modulation is what the process, everything we have been studied. And this whole total we call it as a transmitter. The after vector transmitter, Sx or Xy St, that is the thing, and then Si of t, Sx of any function, the modulation function, which is of a For example, we say it as a, for example, is a function of some carrier signals, like that it may be there. So this is how the function we can take. After that it is passed on to the channel there, and then the noise W of t, which you call as additive white Gaussian noise, which we say is a free noise every time with you is been given to the channel there, and then Si of t plus W of t constitutes the X of t. Then it is given to the detector, detects the signal whatever is there, and separate it into different thing here in the vector receiver, x y z plane, x y z, anything it might be there. So whatever is multiplied has been again given there, and that we called as the receiver part. Then it has been estimated of a symbol w. So it estimates the signal, the different plane, the data has been taken, estimates it, and it gives the data. So this is how we do it. So in short, I explained. Now we'll see the terminologies there. The source output consists of a sequence ones and zeros with each binary symbol being emitted every TB seconds. The transmitting part of the digital communication system takes the ones and the zeros emitted by the source computer and encodes them into distinct signals denoted by S1 of t and S2 of t respectively, which are suitable for transmission over the analog channel. Both S1 of t and S2 of t are real valued energy signal as shown by EI is equals to integration of 0 to TB of Si of t the whole square into dt, where I is 1, 2. This is we call justify it with the equation 1. The received signal is defined by x of t is equals to Si of t plus W of t, where it is ranging from 0 to TB, t 0 less than or equal to t less than to TB, less than or equal to TB. I is equals to 1, 2, and this is because of equation 2. This is W of t, where W of t is the channel noise, as I am told it earlier. Next, this is the AWGN model of a channel. So this transmitter signal Si of t and white Gaussian of W of t is going to add, and that will going to give X of t. So we can just make it as a channel here. The receiver has the task of observing the received signal X of t for a duration of TB seconds and then making an estimate of the transmitted signal Si of t, or equivalently the ith symbol I is equals to 1, 2. Because of the error introduced in the channel, the receiver will make occasionally errors. Hence, it is required to design the receiver so as to minimize the average probability of symbol error, defined as PE is equals to pi 1, probability of M cap is equals to 0 or 1 cent probability, plus pi 2, the probability of M cap is equals to 1 or 0 cent. This is equation 3, where pi 1 and pi 2 are the prior probabilities of a transmitting symbols 1 and 0 respectively, and is the estimate of the symbol 1 or 0 sent by the source, which is computed by the receiver. Now this probability of M cap is equals to 0 or 1 cent, and probability of M cap is equals to 1 or 0 cent are conditional probabilities. In order to minimize the average probability of errors, symbol error, between the receiver output and the symbol emitted by the source, and make the digital communication system more reliable, the following two basic issues are considered. First one, how to minimize the design of the receiver so as to minimize the average probability of the symbol error. Then this is the second one. This should be a second point. Okay, so now how to choose the set of signal S1 of t, S2 of t, dot up to Sm of t, capital M of t, for representing the symbols M1, M2 up to M capital M, M of M, capital M respectively, where M array symbol denoted by M1, M2, so on up to M capital M. Now, the geometric representation of a signals. The essence of we are going to here what is that we are whatever we studied was a basic. Now we are going to actually represent the signal in a geometric form. Geometric means how to represent in a three-dimensional kind of. So the essence of geometric representation of signal is to represent any set of m energy signals of like Si of t as linear combination of n orthonormal basis function where n less than m. That condition has to be there. That pi 1 of t, pi 2 of t, so on up to pi n of t form orthonormal function or basis function that is given a set of real valued energy signals S1 of t, S2 of t, so on up to S capital M of t, each of duration t second. We write Si of t is equal to summation of j is equals to 1 to capital N of Sij into pi j of t, where it lies in the range of 0 less than or equal to small t less than or equal to capital T, and I is equals to 1 comma 2 up to capital M. This is equation 4, where the coefficient of the expansions are defined by Sij is equals to integration of 0 to capital T Si of t into pi j of t into dt. I is equals to 1 comma 2 comma up to capital M. J is equals to 1 comma 2 comma up to capital N. This is equation 5. The real valued basis function pi 1 of t into pi 2 of t so on up to pi n of capital N of t form an orthonormal set by which we mean the integration of 0 to capital T pi I of t into pi j of t into dt is equals to delta ij, that is equals to 1 if I is equals to j, and it is 0 if I not equal to j. That's equation 6, where delta ij is the Kronecker delta. Delta ij is the Kronecker delta. That is, the equation 6 states that each basis function is normalized to have unit energy. Also, the basis function pi 1 of t, comma pi 2 of t, so on up to pi capital N of t are orthogonal with respect to each other over the interval 0 less than or equal to t less than or equal to capital T. Now, for the prescribed I, the set of coefficients Sij, which is ranging from j is equals to 1 to n, may be viewed as an n-dimensional signal vector denoted by Si. The important point to note here is that the vector Si bears a one-to-one relationship with the transmitted signal Sit. Now, some points has to be considered. Given the n elements of the vector Si operating as an input, we may use the scheme as shown in the figure 3a to generate the signal Si of t, which follows directly from equation 4. This figure consists of a bank of n multipliers, with each multiplier having its own basis function followed by a summer. The scheme of figure 3a may be viewed as a synthesizer. Conversely, given the signal Si of t, that is I is equals to 1 comma 2 so on up to capital M, operating as input, we may use the scheme shown in figure 3b to calculate the coefficient S1 of t, comma S2 of t, so on up to S capital M of t, which follows directly from equation 5. This second scheme consists of a bank of n product integrators or correlators with a common input and with each one of them supplied with its own basis function. The scheme of figure 3b may be viewed as an analyzer. So this is the diagram. What we have to be considered that Si1, Si2 and S up to Si of n. N number of sequences can be considered here, which has to be summed with a particular basis function pi 1 of t, pi 2 of t, so on up to pi n of t. Then it is again summed to get it a Si of t. This is we call it as a synthesizer And next one is when this output of the synthesizer will be given to the analyzer. Again, it is not multiplied with the pi 1 of t, pi 2 of t, and pi n of t. So to cancel off this basis function effect there. Then again we estimated it up to the SI1 up to SI2. This is we get a SI of n, SIN. So this is the block diagram of a synthesizer and also the analyzer set. So the next one, accordingly, we may state the each signal in the set Si of t is completely determined by the signal vector. That is, Si is equals to Si1, Si2, so on up to Sin, where I is equals to 1, 2 up to capital M. This is equation 7. If we conceptually extend our conventional notation of 2 and 3 dimensional Euclidean spaces to an n dimensional Euclidean space, we may visualize the set of signal vector Si of I is equals to 1, 2 up to so on up to M as defining corresponding set of M points in an n dimensional Euclidean space with n mutually perpendicular axes labeled pi 1, pi 2 up so on up to pi n. This n-dimensional Euclidean space is called the signal space. It provides the mathematical basis for the geometric representation of energy signals in a conceptually satisfying manner. This form of representation is illustrated in the figure 4 for the case of a two-dimensional signal space with the 3 signals, that is n is equals to 2 and m is equals to 3. So we have considered 2 signals and with having a 3 dimensions there. In an n-dimensional Euclidean space, we may define the length of a vectors and angle between the vectors. It is customary to denote the length, which is also called as the absolute value of or norm of a signal vector Si by the symbol mod of Si. The squared length of any signal vector Si is defined to be the inner product or dot product of Si with itself as shown by mod of Si the whole square is equals to Si transpose into Si, which is also can be written as equal to summation of j is equals to 1 to capital N into Sij the whole square, where I is equals to 1, 2 up so on up to M, where Sij is the jth element of Si and the superscript T, capital T, denotes matrix transposition. Now, what we had discussed in the previous slide, the figure 4, is this one. It is having a signal S1, S2 and S3, which have been differentiated in the 2 domains, pi 1 and pi 2, and it has a 3 different signals. That is trying to say that m is equals to 3 and it is having a n is equals to 2. By definition of the energy of signal, Si of t of duration t second is given by capital EI is equals to integration of 0 to capital T of Si the whole square, Si of t on the whole square into dt. I is equals to 1, 2 so on up to capital M. This is equation 9. Therefore, substituting this equation 4 into equation 9, we get EI is equals to summation integration of 0 to capital T of summation of j is equals to 1 to capital N into Si of j pi j of t. Then again the summation of k is equals to 1 to capital N Sik into pi k of t into dt. Interchanging the order of the summation and integration as both linear operations and then rearranging terms, we get EI is equals to summation of j is equals to 1 to capital N summation of k is equals to 1 to capital N into Sij into Sik integrated from 0 to capital T of pi j of t into pi k of t dt. Since by definition the pi j of t form an orthonormal set in accordance with the two condition of equation 6, that is, we find that equation 10 reduces simply to capital EI to summation of j is equals to 1 to capital N into Sij the whole square, that is equals to Si mod of Si the whole square. That is equation 11. Here equation 8 and equation 11 show the energy of any energy signal Si of t is equal to the squared length of the corresponding signal vector Si of t. In the case of a pair of signals Si of t and Sk of t represented by the signal vector Si and Sk respectively, we may also show that the integration from 0 to capital T of Si of t into Sk of t into dt is equals to Si transpose into Sk. This is equation 12. Here the equation 12 states that the inner product of the energy signals Si of t and Sk of t over the interval 0 to capital T is equal to the inner product of their respective vector representation Si and Sk. Note that the inner product Si transpose of Sk is invariant to the choice of basis function pi j of t, which is from j is equals to 1 to capital N, in that it only depends on the components of the signal Si of t and Sk of t projected onto each of the basis function. Another useful relation involving the vector representation of the energy signal Si of t and Sk of t is described by mod of Si minus Sk the whole square, that is equal to summation of j is equals to 1 to capital N of Sij minus Skj the whole square, that is equal to integration from 0 to capital T into Si of t minus Sk of t the whole square into dt. This is equation 13, where Si minus Sj mod of Si minus Sj is nothing but the Euclidean distance dik between the points represented by the signal vector Si and Sk. To complete the geometric representation of energy signal, we need to represent for the angle theta ik subtended between two signal vectors Si and Sk. By definition, the cosine of this angle theta ik is equal to the inner product of these two vectors divided by the product of their individual norm, as shown by cos of theta ik is equals to Si transpose Sk divided by mod of Si into mod of Sk. That's equation 14. The two vectors Si and Sk are thus orthogonal and perpendicular to each other if their inner product is 0, in which case theta ik is equals to 90 degree. So cos 90 is equals to 0. So it is trying to say when there is a ik is equals to 90 degree, it is trying to say they are either orthogonal or perpendicular. So that time this product will be a 0. This was about the brief introduction of the why digital systems and why digital system. Then again we had a brief introduction of a digital communication system, so we can have an idea how this vector representation is required, the basis all were there, and at the end we took a two signal which of n is equals to 2 and m is equals to 3, that condition, and we plotted it in the on the geometric way on a plane of pi 1 and pi 2 basis function, and we represented it. On that basis we defined how the condition of if a two signals has been there, how they represent each other, and what are the condition by at the end of this discussion, that was at the equation 14. So this all were the criteria which we need to be considered while doing the geometric representation. So here we conclude the whatever we have done here. Okay, thank you.